For decades, the performance car world was built on one sacred belief. If you wanted control, speed, and emotion, you needed metal. You needed a steering column you could feel through your wrists. You needed anti-roll bars thick enough to fight the weight of the chassis. You needed a mechanical differential, grinding away beneath the floor, trying to rescue traction, after physics had already started winning. That was the old religion of Stuttgart Maranello and Woking. But the Denza Z Spider arrives as something very different. Not just another Chinese electric sports car. Not just another 1,000 horsepower headline designed to shock the internet. This machine is a warning shot aimed directly at the foundation of European performance engineering. Because its real threat is not acceleration alone. A sub-2-second sprint is brutal, but it is not the full story. The deeper threat is architectural. Steering is becoming data. Suspension is becoming chemistry. The battery is becoming structure. The differential is becoming software. For the first time, the old mechanical formula is not being improved. It is being replaced. And that should worry every automaker that still believes heritage can defend itself against computation. The most dangerous part of the Denza Z Spider is not that it looks unfamiliar. It is that it looks dangerously familiar. This is not a machine shaped like a laboratory experiment. It does not arrive with awkward proportions, exposed technology, or the cold visual language of an engineering prototype. It arrives wearing the emotional costume of the European sports car, a low stance, a long visual line-wide rear shoulders, and the kind of open-top silhouette that has been used for decades to sell freedom, speed, and taste. That is what makes it so disruptive. Denza is not rejecting the romance of European performance. It is absorbing it, translating it, and then hiding a completely different operating system underneath. The surface speaks the language of Monaco, Goodwood, and the Italian coast. But the architecture underneath speaks the language of sensors, processors, actuators, torque maps, battery structure, and high voltage control. This is why the car feels less like a competitor and more like a Trojan horse. It does not attack Europe by looking alien. It attacks Europe by looking beautiful. It borrows the emotional vocabulary that made old-world performance desirable, then uses that beauty to smuggle in a new definition of speed. One where the soul of the machine is no longer a crankshaft, a steering column, or a mechanical differential. It is computation wearing a designer suit, and that is far more dangerous than brute force. To understand why the Denza Z Spider matters, you have to begin at the oldest contract between driver and machine, the steering wheel. In a traditional performance car, that relationship is physical. Your hands turn the wheel. The wheel turns a shaft. That shaft runs through the firewall and reaches the steering rack. From there, metal moves metal. It is direct, familiar, and emotionally powerful. For decades, that mechanical link was treated as proof of authenticity. But it also came with limits. A steel steering column adds weight. It transmits vibration, road harshness, and structural noise into the cabin. More importantly, it locks the car into a fixed mechanical ratio. At parking speed, track speed, and highway speed, the system is still trapped inside the geometry of gears and linkages. The Denza Z Spider attacks that entire premise. With steer-by-wire, there is no physical column tying the steering wheel to the front axle. The driver turns the wheel, but the movement becomes information. Sensors read the input, convert it into digital telemetry, and send commands to actuators controlling the front wheels. That changes everything. At high speed, the system can calm the steering response, filtering tiny movements that could destabilize the car. In a tight corner, it can sharpen the ratio, allowing a small hand movement to create a much larger tire angle. The steering is no longer one fixed mechanical compromise. It becomes a variable software decision. And that is why the folding steering wheel matters. It is not just theater. It is physical evidence that the steering column no longer owns the space between the driver and the road. For legacy engineers, that is an uncomfortable thought. Because once steering becomes data, the old argument about mechanical purity begins to collapse. The question is no longer how beautifully metal can transmit force. The question becomes how fast, how accurately, and how intelligently a digital system can interpret intent. That is not a small upgrade. That is a philosophical rupture. Once steering becomes digital, the next battlefield is the body itself. Because a 1,000 horsepower car does not fail only because it lacks power. It fails when the chassis cannot control where that power goes. Under hard acceleration, braking and cornering mass becomes a weapon pointed against the car. The body wants to roll. The tires want to overload. The suspension has to fight a moving storm of kinetic energy. The old solution was mechanical resistance. European performance cars use thick anti-roll bars, complex dampers, and later active air suspension systems to keep the body under control. But air has a weakness that no badge can erase. It compresses. A pneumatic system needs time to read the load, adjust pressure, move air, and settle the car. In performance driving, even a few hundred milliseconds can feel like a lifetime. The Denza Z Spider moves the fight into a different layer of physics. Its DiSus-M system does not simply push more air into a chamber. It uses magnetorheological dampers filled with a special fluid containing microscopic iron particles. In normal driving, those particles move freely, allowing the suspension to absorb rough pavement and small road imperfections. The car can remain calm, comfortable, and controlled. But when the sensors detect lateral force, pitch braking load, or sudden weight transfer, the system changes character almost instantly. Electrical current passes through electromagnetic coils inside the dampers. The iron particles align under the magnetic field, and the fluid rapidly shifts from soft to resistant, almost as if the damper has changed its physical personality. That is the crucial difference. A traditional suspension reacts to motion. This system prepares for force. It can stiffen the exact corner of the car that is about to take the load while keeping the rest of the chassis composed. Instead of letting the body roll and then trying to correct it, the system attacks the problem at the material level. This is not just suspension tuning. It is real-time control over how matter behaves inside the damper. For legacy performance engineering, that is a serious threat, because the old world solved body control with bigger metal, stronger bars, and heavier hardware. Denza is suggesting a different future, one where the car does not merely resist physics with mass, but rewrites the response using sensors, electricity, and controlled chemistry. That is when suspension stops being hardware. It becomes computation passing through liquid metal. But even the smartest steering and the fastest suspension mean very little if the body underneath them cannot survive the load. That is the hidden engineering problem behind every open-top performance car. The moment you cut the roof away, you remove more than a piece of styling. You remove a structural bridge. In a coupe, the roof helps tie the front and rear of the vehicle together. It resists twisting. It helps the chassis stay precise when the car is braking, cornering, or launching under heavy force. A convertible loses that advantage. That is why traditional convertibles often require extra bracing underneath the body. More steel, more reinforcement, more weight. The car becomes safer and stiffer, but it also becomes heavier, slower to respond, and less pure in its movement. The Denza Z Spider uses a different answer. Instead of treating the battery pack as a heavy box that must be carried by the chassis, it turns the battery into part of the chassis itself. Through cell-to-body architecture, the pack is integrated into the structural floor of the vehicle. The casing is no longer just protection for the cells. It becomes a load-bearing spine. That matters because the battery sits low, wide, and central. In an electric convertible, this is not just a source of energy. It is a structural weapon. It helps resist torsional flex when the car is thrown into a corner. It helps keep the body from twisting under the violence of a hard launch. It allows an open-top design to maintain the kind of rigidity that older convertibles had to chase with added metal. This is where the EV architecture becomes more than a drivetrain change. In the old formula, the engine powered the car and the frame carried the car. In this new formula, the energy system helps hold the car together. The battery is no longer dead mass. It becomes part of the performance equation. And that is a problem for every legacy platform still trying to adapt electric power onto bodies designed around combustion logic. There is another contradiction hidden inside the Denza Z Spider, the cleaner. It looks the more violent its engineering becomes. An open-top performance car is beautiful because it removes the barrier between the driver and the outside world. But from a safety perspective, that beauty creates a brutal problem. At very high speed, with no fixed roof above the occupants, a rollover is not just a crash event. It is an existential failure of the entire vehicle structure. Traditional engineering usually solves this with visible reinforcement, thick windshield frames, heavy fixed hoops, structural compromises that remind you the car is fighting against its own missing roof. The Denza Z Spider takes a different route. Its active roll bar system is hidden behind the headrests buried inside the rear bodywork, where it does not interrupt the silhouette. Under normal driving, the car remains clean, elegant, and almost theatrical. But if the sensors detect the beginning of a rollover event, the system changes instantly. Pyrotechnic mechanisms deploy the protective bars in milliseconds, turning a hidden safety structure into a last-second survival cage. That is the real character of this machine. It presents beauty on the surface, but underneath it is constantly measuring risk, calculating motion, and preparing for violence before the human body even understands danger has arrived. The next piece of old-world hardware under attack is the mechanical differential. For more than a century, performance cars have depended on a physical chain of force. The engine produces torque, the transmission reshapes it, the drive shaft sends it backward, the differential splits it between the rear wheels. In a good car, that system can feel magnificent, but it is still a compromise built around physical delay. A traditional limited slip differential is reactive. It waits for a difference in wheel speed. It waits for traction to begin slipping away. Then through clutches, gears, fluids, or electronic commands, it tries to redistribute torque before the corner is lost. The Denza Z Spider removes that entire mechanical argument. Through its E3 architecture, the car uses a tri-motor layout with two independent motors controlling the rear wheels separately. That means the left rear wheel and the right rear wheel are no longer prisoners of the same axle, the same differential housing, or the same mechanical compromise. They can receive different torquey commands at the same moment for different purposes. This is where the physics begins to feel almost unfair. Imagine the car entering a fast corner with massive lateral load moving across the chassis. In an older performance car, the front tires must fight understeer. The rear differential must manage traction, and the driver must balance throttle with steering input. In the Denza Z Spider, the software can intervene at the wheel level. The outside rear motor can push forward with positive torque, helping rotate the car through the curve. At the same time, the inside rear motor can apply negative torque through regenerative braking, dragging that side of the vehicle just enough to create a controlled yaw moment. The result is not merely grip. It is rotation manufactured by mathematics. The car is no longer waiting for a mechanical differential to rescue traction. It is using opposing forces across the rear axle to pull its own nose toward the apex. It can make mass behave as if it is smaller than it is. It can make a heavy, high-powered electric machine pivot with a kind of artificial agility that old hardware cannot easily imitate. This is why the threat is bigger than one sports car. If software can generate rotation faster than a mechanical differential can react, then one of the sacred tools of performance engineering becomes secondary. The limited slip differential does not disappear overnight, but its authority begins to fade. Because in this new formula, handling is not just a property of suspension geometry, tire compound, and driver skill. Handling becomes a calculation, repeated thousands of times per second. And once that happens, the battlefield moves away from who can machine the finest gears, and toward who can write the fastest control logic. But there is one final enemy that every extreme performance EV must face: heat. A 1,000 horsepower electric car can produce violent acceleration for a headline. That part is no longer shocking by itself. The harder question is whether the car can keep that power alive when the battery, motors, inverters, and cooling systems are all being pushed near their limits. An electric performance heat is the silent executioner. It does not need drama. It does not need smoke. It simply raises temperatures until the software begins cutting power to protect the hardware. That is thermal throttling, the moment when a car's numbers look terrifying on paper, but the system cannot sustain them under repeated stress. The Denza Z Spider has to solve this problem under an even more difficult condition. It is an open-top car. Without a fixed roofline, airflow becomes harder to control. The cabin interrupts the stream. Downforce becomes more complicated. Cooling pathways must be shaped with more precision. That is why the rear of the car matters so much. Instead of relying only on a large drag-heavy wing, the design uses a massive rear diffuser to generate downforce from underneath the vehicle. The goal is to create a low-pressure zone that pulls the car toward the road without destroying efficiency at high speed. At the front, the hood extraction channels are not decoration. They are pressure management. They help pull hot air out of the cooling modules, reducing heat buildup around the systems that keep the motors and power electronics alive. This is the part of the car that separates spectacle from endurance. Acceleration is the explosion. Thermal management is the discipline that decides whether the explosion can be repeated. For Denza, 1,000 horsepower is not just a power claim. It is a test of whether Chinese EV engineering can manage airflow temperature and voltage with the same seriousness that Europe once applied to combustion oil temperature and mechanical cooling. Because speed is not only about creating power, it is about preventing power from destroying itself. The Denza Z Spider is not important because it is fast. Speed has always been part of the performance car story. Europe knows how to build fast cars. America knows how to build fast cars. Japan knows how to build fast cars. A headline number alone does not rewrite an industry. What matters is the formula behind the number. The Denza Z Spider is attacking the mechanical assumptions that shaped high-performance vehicles for generations. Steering no longer requires a steel column. Body control no longer depends only on heavier bars or slower pneumatic systems. Convertible rigidity no longer has to be rescued by added bracing. Rear wheel rotation no longer has to wait for a mechanical differential. Even aerodynamics and cooling are being reorganized around the demands of high-voltage electric power. That is the real warning. Europe did not simply face another electric rival. It faced a different definition of performance, one built from sensors, actuators, battery structure, magnetic fluid software, torque vectoring, and thermal discipline. The old world believed performance was something you machine-tuned and perfected through heritage. The new world is suggesting something far more uncomfortable. Performance can be calculated, updated, and controlled in real time. That does not erase Stuttgart Maranello or Woking overnight. But it does change the question they now have to answer. If the future of speed is no longer ruled by the purity of mechanical connection, but by the intelligence of computation, then the next great performance war may not be won in the engine bay, the gearbox, or the differential housing. It may be won inside the control logic. And that is exactly where the old empires are most vulnerable.